Hello, I'm Chance Hattrick, and this is my video for the AVR assembly Double Dabble. So this is the output of the Double Dabble, and so when I rotate the potentiometer to the left, you can see the value is decreasing. If I keep it still, you can see it remains at the same value, and I can continue to decrease it until it reaches 0. Then I can move it a little bit more to the right. You can see it start to increase. And I can turn it all the way to 1023. And you can see it stays at that value, and you can see that the digit 4 of the BCD value here remains at 0 because the maximum value is only 4 digits. So here we have the assembly code for our Double Dabble circuit. You can see here that we're inputting these prescalers for the timer 1 and the ADC. Then we define our variables that will be used for the Double Dabble. Then we define the values for the bits that are required for the serial printing. And finally, we define the registers for the different digits, bin 0, bin 1, as well as the digits for the BCD counter. We then define the origin for the start of our interrupt vector table, and then which is the table that defines different commands that can be used as interrupts for the timer 1, timer 0, EEPROM, ADC, etc. And then we jump to, we define an origin for our assembly code at line 0200, which ensures that our code does not overlap with the vector table, which could lead to issues. We then go to main and call IO setup, which defines pin 13 as the output for our built-in LED. And then we go to timer 1 setup. And at timer 1 setup, we prepare the timer 1 in normal mode, which disables PWM. And then we use that timer 1 prescaler as defined in our .h file in order to slow down the frequency of the timer 1 to 60 Hertz, which speeds up the amount of time it takes for each interrupt to occur. And then we enable the timer overflow interrupt, which is used to indicate when the ADC should begin conversion, which is seen in the interrupt here. Afterwards, we then go to ADC setup, which defines the timer 1 as the automatic interrupt or flag that is used to trigger the ADC, which then causes it to call the ADC vect, which inputs the output of the ADC to bin 0 and bin 1, and then sets a flag to tell the nano that the data is ready for the Double Dabble, and finally it toggles the LED on. After this has been set up, we initiate the USART, which is used for the serial communication. We check to see when the ADC flag is on, at which point we initiate our main loop, as seen here, and then we go to the Double Dabble function, which you can make found here. Here, the first thing we do is we clear the bits of the BCD for the next Double Dabble, and we redefine our variables. Then we go to Double Dabble high, which is the bit 1 of the BCD. We check to see if it's less than or equal to 5. Sorry, if it's greater than or equal to 5. If it is greater than or equal to 5, then we go to the BCD 01 low, which is pin 0. If it is, then we add 3 to the BCD 01. If it is greater or equal to 5, we add 3 to the BCD 01 for that bit. And then we go to the next digit, which is digit 0, which we do the same thing. And we do this for every single digit of the BCD before we then shift all the BCD values. And then we check to see if 16 shifts have occurred. If not, then we go back to the high. After these 16 shifts have been completed, we then go to display, which changes the BCD values into their ASCII equivalents, which is then printed on the serial monitor through the use of the TXChar and the RXChar commands. And finally, we'll see our output. Afterwards, we delay for a single second and we start the whole process again.